Uh, Good morning, everybody. Appreciate you here. I'm Wes Blocher from Siemens. I'm an instrument and controls guy. I've been with Siemens for 21 years. Been in the industry kind of pushing 40. So I've been doing this a little while. What you're seeing there says PID Basics, and that's what it's going to be. This is pretty basic what I'm going to go through. We're going to take about an hour, kind of hit the high points. If you're new to PID control or control at all, don't let this freak you out. People write books about this stuff, okay? This is a subject that you can learn as much as you want to learn. You're never going to know it all, okay? But we're going to give you a good place to start. If you're an old guy like me, hey, listen in, you might learn something. I've been doing this since the pneumatic days, and we're glad to answer your questions. And like I said, we're going to go through this, and when it's all over, if there's questions you have, I'll be glad to answer them. If a week from now you need something, the Gilson guys will be happy to step in and help you with this. As far as control goes, we're Siemens. We do a lot of control. We can help you on any level you need help. So with that said, I'll launch right into this thing. And like I said, if this is all new to you, don't freak out. This is just a start. All right, here's what we're going to try to do today. We're going to learn the basics of PID control, what it is. We're going to look at this and say, okay, we have loops out here. What are the characteristics and the selection criteria for the actuators, the instruments, things like that? What pitfalls are you going to see? What are you looking for here? And where are the landmines? Because they're out there. And the typical process and the type of control strategies that need to be employed. Okay, it says at the end, test and evaluate several process model function blocks. We're not going to do that. The reason I left that on here was that's kind of the way real high level control works. People generally in the DCS world or the software world, even the high level single loop world, you don't just put a controller in there, turn it on and hope it works. You know, most of this, the higher level stuff, it comes with process software where you can simulate things and you can say, okay, if I do this or I do that, how does that really affect my process before it affects your process? Okay. What the slides you're going to see here are part of a presentation or part of training I do internal for Siemens. This is an 8-hour class. And even in the 8 hours, I can't hit everything. Okay. But like I said, I just want to leave that in there to let you know there's higher level things that a lot of people do. All right, the session one, what we're going to start out with today is what is PID control? You hear PID this, what does that stand for? What does that mean? And why is it important and who uses it? Okay, the other thing is designing the process and sensor actuator selection, the sizing, the scaling, the accuracy. Okay, I've got a control system, but it's a system. It's not just a controller. It's not just a DCS system. That loop is a system. That loop of control, there's many parts of that that have to function together, and they have to function right, or you're just wasting your time. All right, section 2, we're going to talk about setting this thing up. I've got the controller. What happens? What do I do? Where do I start? Well, what does all this mean? And temperature control is a basic strategy. Reason being is, as I'll go into later on, temperature control is the single most common control in control. That's kind of where control started. It's the easiest thing to control by and large, and it was first. And this is pre-microprocessor, okay? This is pre-anything. When I learned control, it was pneumatic. Yeah, I know people laugh at that, but that's the way it was at the time. And then when it became electronic control, that was a big step, but that was still pre-microprocessor. Okay, it was now electric, but you had to do all the tuning yourself. No microprocessor, no auto tune. Things have changed, thank God. All right, the other thing is I've got the loop and I'm running this loop. Okay, everybody's happy. How do I dial this in? What do I change? What am I looking for in this loop? Okay. That's the customizing that loop. That's the tweaking of the loop. And sometimes you can auto tune a loop, push the button, life works, life's good, and you're done. Other times you can auto tune, but we don't live in a perfect world. You auto tune, but things aren't exactly dialed in. That's what the customizing is about. That's when you've got to go kind of tweak things to see if you can get a little tighter control, a little better control, whatever it is you're looking for, maybe a little faster control. Okay. But remember, when you're tuning a loop of any control, things are tied together. I can't speed it up without, maybe I lose a little resolution. Maybe I want it a little more accurate, but that requires slowing it down. Okay. Everything's tied together. I can't change a variable in this PID loop without affecting everything else. That's just the way it is. And yes, there's a trade-off. And yes, there comes that point in time when you got to say, okay, this is as good as it gets for me. For this loop, this is as good as it gets. Is it perfect? It never is. But that's what optimization, that's what customizing is all about. It's a trade-off. All right. Now we're going to look at engineering units and loop normalization and real world versus normalized inputs. Okay, the real world works a little different than the math book works. The theory's great, but there's only so far that goes in the real world. You see that there, it says loop algorithm options. What do they do and why are they there? Well, that's an excellent question. We're going to get into a little bit of that, but you could write a book. I mean, it's a physics lesson to get into a loop algorithm. Okay. Why? Well, because now in the world of microprocessors and Autotune, it's kind of a form, well, I think that's not true. It is a form of artificial intelligence. Okay. The Autotune algorithm is the expert operator. Okay. I'm going to put this expert operator in charge of tuning my loop, and I'm going to take his word for it. That's kind of what you're doing. Now, he's an expert, but he can only deal with what he has to deal with, the quality of the information coming back to him and things like that. Now, also, this is still math. It's still an algorithm and only goes so far. It only takes so many things into consideration, and that's as far as it can go. Now it's up to you. You may have to say, okay, expert operator, appreciate the help, but I may have to tweak a little bit. And that's where things in the control business get a little fuzzy, okay? Because people say, well, I'll push the auto-tune button and that'll be great. Well, good, sometimes, not all the time. And the more complexity you have in this control loop, the less that's going to be so, okay? That's just the way it is. I don't want to scare anybody, but I'm just saying, don't expect to always push auto-tune and have it auto-tune and walk away. And we're going to go into some of that those other things in just a second. Okay. The other thing, which we're going to hit on very, very briefly, is when I talk about control, I'm talking modulated control, digital. Most of the time, it's a 4 to 20. Okay. My control loop is I'm opening and closing a valve or something like that for a level, for a temperature, for a flow, for a pressure set point that I'm going after. There are other things in the real world. There's step and pulse things. There are things that, for reasons I don't always understand, it's like a bakery. You go to a commercial bakery and they're baking loaves of bread on a giant conveyor. They're controlling that temperature with a step. There's a little electric actuator and it opens a gas valve. So it makes the oven hotter or less hot or whatever. And it click, 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 click. They don't generally ever modulate the way I would. Why? That's just what they've always done. Is it the best? Hey, I don't know, but it works for them. So when somebody says PID control, in the vast majority, it's going to be some, what I call analog signal. Then it may be Profibus, it may be field bus, but you're also going to run into applications where the controller's pulsing or just stepping. Is it bad control? No, it works for those guys. Okay. And we're going to talk about why you pick some of that stuff in just a minute. All right. We'll take a jump in this. So here's the textbook. It's pure math, man. Not a problem at all. In this la-la land, the controller instantaneously gets a signal from the field and instantaneously makes a change right to set point, and everything's good. And it's lots of decimal places mathematically. Well, I don't know where this what planet this is, but that's not how reality really works. We all know that what's next? Well, I got to deal with the environment. I've got to deal with flows that change and pressures that change and temperatures that change and lag in the system. My controller tells a valve to open. That's not instantaneous. A valve has to take some time for it to open. It takes time for a flow meter to respond to that flow. And people say, well, that's not very much time, but that's true, but it's there. And it has to be dealt with. Mathematically, the controller has to deal with that. Okay? And if it can't deal with that, it's going to be unstable. You're going to have a loop that's bouncing around and chasing itself. Okay? What that means is, in the real world, there is inherent deadband in the system. Sorry, that's just the way it is. It's a law of physics. There's no way around that. Be it little, be it a lot, it's there. And part of what the controller is dealing with is that deadband. And we're going to talk about what happens when it can't deal with that deadband. All right. What we call actuators, which is a word we use in the control world, it's what am I doing? Okay, the controller itself, be it a single loop controller or a card in a DCS or some sort of software laying on top of a PLC, okay, it's doing something. It's telling something to do something. It's turning a motor on and off. It's turning a fan on and off. It's repositioning a valve. It's turning something on and off, or it's modulating something. Okay, that's what it's doing. So the controller is telling something to do something and getting the feedback from some instrument or sensor to let it know, yes, I'm on set point, quit doing that, or I need to open that valve, or I need to speed the fan up or turn the fan on, or whatever it is I have to do. That's what we're all talking about here. Okay? Okay. Now, the sensors, what our friends at Gilson are good at, very good at, is sensors. Well, that's an instrument. What are you measuring? What is it you're really trying to do? The first question in any control is, what are you trying to do with this mess? Well, I'm trying to control flow, or I'm trying to control pressure, I'm trying to control temperature, or I'm trying to control 2 or 3 things. I'm trying to control a temperature, but I don't want the flow to exceed something. Okay? And then you get, let's say, specialty measurements, pH or salinity. Well, why is that special? Those are very hard to control. It's not like a pressure or flow. It's not a matter of just opening a valve. There's a lot to that. And that's where, when somebody says PID control, well, what does that mean? Am I controlling something very, very simple, like the air conditioner in my home? Or am I controlling something that's hard to control and hard to measure, like pH? That's more complex control, which we're going to talk about. Okay. Now, if you came to me and you said, hey, Wes, I want to control pressure, temperature, whatever it is, the key specs, that's what I'm going to ask you. Okay? What is it we're trying, to what accuracy? If you say, look, I want to control this tank level here, and I don't care if it's way off, I just want to make sure the tank doesn't run dry or doesn't run open. Well, anybody can do that. That's easy. You come to me and you say, well, I want to control this temperature in this reactor to 1/10 of a degree Fahrenheit. That's a whole different conversation. That's a whole different level of control. It might not even be possible. Just because somebody wants it doesn't mean it can be done with what they have, or may not be done at all. It just might not be there, okay? But I'm going to ask these questions. What are we really looking at? And I'm going to look at your process. Things like pH and like salinity are horribly nonlinear. It's not like you add a little something and there's this change that follows. That doesn't work. That doesn't happen in the real world most of the time, okay? And you look at things like span. If you're trying to control at 70 degrees plus or minus 5 degrees, that's fine. If you're trying to control to 70 degrees plus or minus 1/10 of a degree, different conversation. Can it be done? Possibly. But it's going to be a whole different conversation, a whole different complexity of controls to do things like that. Expectation, you got to kind of go in there. Let's make sure the expectations of what we're all trying to do here are realistic. If I've got a flow meter that on its best days, a 0.5% device, and you're talking about 0.1%, hang on, we need to talk about that. Also, if you're telling me that you want 0.1% or 1/10 of a degree or whatever it is, first question I'm going to say is, how do you measure that? Can you measure that? How reliably can you measure that before you really get deep into it? Because the last thing you want is to put a system in or try to tune a loop that's just never going to make somebody happy. All right. Measuring temperature. That's about, seriously, people argue this point, it's about 80% of control. This is some sort of temperature. Somewhere down the line, there's a temperature loop. Okay? And most people do that with a thermocouple, RTD, or whatever. And what do you have to do? Well, I've got to get the right stuff in there. I've got to put it in the right place. I've got to make sure the wiring's correct. I've got to do a lot of things to get the best temperature measurement I can get. My control is based on what those sensors tell me. The controller system or whatever you have it can only be as good as the information coming in. I've got a bunch of sensors out there that are in the wrong place, the wrong range. They're not wired right, so I'm getting a lot of extra effect, maybe bad wiring, maybe noise. The system doesn't have a crystal ball. It's just going to take that information with the assumption that it's correct, run it through the algorithm, and give you an output to control. If that's okay, the expectation is it's going to control. It's not. And you're not going to tune that out either. And we're going to talk about that. All right. Now let's get in the meat of this thing. PID, proportional integral derivative, that's just a type of action used to control modulating things, valves and dampers and variable speed devices. And when somebody talks about a loop, they're generally talking about a closed loop. It's a circle. I've got a controller, some sort of element, and I'm measuring something. I'm controlling that flow, that pressure, that temperature, whatever it is I'm controlling, okay? And PID, we're going to go through this, and basically you're seeing this right here. This is kind of simple, but this is kind of the meat of all control. You know, 100 over the gain, that's proportional band. Integrals, 1 over the reset, that's units of time, and the derivative is rate. Okay, now this bottom part's for anybody on this call that's probably over 60, like me. Most people don't talk about gain anymore. Okay, they talk about proportional band. Gain's kind of the inverse of that. Gain is something that we used in the pneumatic days. That was, people talked about the gain. Well, the gain of the controller needs the gain of this. That's kind of gone now. I don't know anybody really talks about gain. You may hear it a little bit, but again, the guy's probably over 60. So you're going to hear more proportional band. And that's okay. Don't worry about if say this guy from Siemens said something about gain. Well, you're probably never going to hear that. I haven't heard it in years and years and years, unless I'm talking to somebody my age. So don't worry about it. Again, if it pops up, you know what it is. It's just the inverse of band. Most people talk about band these days. In fact, everybody does. All right. Proportional control only. Proportional control only is basically it's a one-dimensional thing based on the control signal between the actual condition and the set point. That's called error. So the difference, like it says here, the difference between actual condition and the set point is the error. Okay, you will have people talk about the error. Well, that's all he's talking about. If my flow meter is telling me I'm getting 300 GPM and I want to open the valve to 400, the error is that 100 GPM. Okay, valve opens, now I'm flowing to 400 GPM, the error is gone, I've corrected the error, everybody's happy, I'm at set point. Okay, now the oldest and most common, I don't know what you call it, example, if you will, of proportion only control is a thermostat in your house. You set it at 72 degrees, it comes up and it turns the air conditioner, heater on, whatever, and it lays around and the temperature changes a little bit and it falls back. Now, it's not the best control, but think about it this way. If you came to me and you said, Wes, by God, I want my air conditioner to keep my house 72 degrees, right on 72. Okay, I put a PID controller in there and your air conditioner is going to go on, off, on, off, on, off, and self-destruct. Proportional control is good for what it's good for. Okay, it's not a matter you have to have all this complexity. You really don't. In fact, in this illustration of your thermostat, tight control would be bad because that constant on-off would your air conditioner would come apart, and it's fine. So it's going to kind of lollygag around. And here is the bottom line. It's probably never, ever, ever going to be on set point. Ever. It'll pass through. It'll overshoot and cool your house down a couple extra degrees. And it's going to start to fall. It'll go right back through set point and fall and fall and fall. Oh, now it's going to turn the air conditioner back on or off, whatever it is. Okay? It's probably never, ever going to be on set point. It won't be exactly 72 degrees at the thermostat. There's a big band in there. It'll be between 74 and 60 something, whatever it is. And that's just the way it's going to be. But that's good for that type of control. A lot of things are proportional only. Again, like your thermostat, most refrigeration, most heating, all that's proportional only. Okay, that small amount of error that's always there, that's called the offset. Okay, that gap, that's the offset. And that's just part of proportional control. That's you're going to have to live with. Now, you want a little tighter control, you add the integral in. Okay, what does the integral do? Now, when I say what does it do, the integral action is part of the algorithm. It's running this mathematical equation, and it says, okay, I'm summing the error, and I'm going to add some control signal. I'm going to tighten this down a little bit to eliminate the offset. That's all I'm trying to do with the integral action. I'm just trying to eliminate the offset here. I'm saying, okay, this is not my thermostat, so I want this offset to be as close to 0 as I can. Am I going to get there? Maybe. On the temperature loop, you probably get there because it's slow. We're going to talk about slow. We're going to talk about fast. You're probably not going to dial dead on. Again, like we talked earlier, what's your resolution? If you're talking about a couple of degrees, you're good. If you're talking about 1/10 of a degree, I don't think so. You're probably never going to be dead on it all the time. But that's what proportional does. You're trying to kind of keep that offshoot as low as you can. All right. Here's what proportional and integral. Here we're going to talk about this. Most loops out there are PI only. People say, whoa, wait a minute. I've got a derivative. It's not on 0, it's something. Well, that's fine. Most controllers now that have any sophistication, most of them do, only turn the derivative on if they need it. It may be there, it might not be 0, but they don't always use the derivative. Why? Well, they don't need it. They don't add that complexity. They don't add that processing time because they just don't need it. Okay? Most of the loops out there are proportional integral only. What does it do? What makes that so good? Well, what it does respond to the error in a control loop pretty quickly. And what that integral really does, it just says there relate the magnitude of the control signal to that error. Yeah, if the bigger the error, the bigger the control signal and the faster it goes. That's what the integral's doing. It says, oh my God, the error is huge. Not only do we want to get to set point, we want to get there as quickly as possible. Again, with still in the control, still without that offset or as much offset. Okay. And it says, what about overshoot, quarter wave decay? Now, I'll bring this quarter wave decay thing in this. What is quarter wave decay? People write books about this, but here's what quarter wave decay is. Quarter wave decay is you go and you overshoot a little, then you undershoot, and these quarter waves, undershoot, overshoot. And after some cycles, it smooths out on set point. Most people don't like that. That's not the worst thing in the world, because if it smooths, think about this. If I'm out there and I'm all over the place, that's one thing. If my quarter wave will finally get to where after, let's say, 5-10 cycles, I'm on set point, at least I'm in the ballpark. I know I can get to set point. Now I can work on taking the quarter wave out. Now I can work on trying to get that little bit of overshoot out. And that's what the derivative does. Okay, that's what derivative does. For all intents and purposes, the derivative is just a braking action. Okay, it's also a time-based thing, but it looks at not the magnitude of the error, but the rate of change of that error. How fast is the control signal going? How fast is it correcting the error? Okay, once it's correcting the error, the derivative looks at that and goes, okay, whoa, we need to brake. We need to stop. We're going to overshoot if we don't slow down here. We're going to go past the stop sign. Okay? The goal of the derivative is strictly to reduce that overshoot. I'd like to say eliminate that overshoot, and sometimes you can. Realistically, sometimes you can't. It just depends on the loop. Okay? Now, the bottom sentence is one of the things you need to take away from this. It will slow the overall response. But again, like we talked about earlier, that's the price you pay for that stability. That's the price you pay for that accuracy. I want this to be dead on. Well, I'm going to have to slow it down a little bit. Again, like I said earlier, the proportional, the integral, derivative are all tied together. They're not independent pieces now. They're all together. They all work together. So I'm going to have to give up a little. And what do I give up for that stability, for that accuracy? I'm going to give up some speed. And that's just the way it is. How much? Well, that's up to you to decide how much you're willing to pay for that stability. But you're going to pay for it. All right.
Hey,
again,
Wes,
yep.
we got some questions that are coming in.
Okay.
The first one, let me find it here. I'm sorry. First one states there is on-demand, adaptive, and continuous auto-tune. Can you explain the differences and why you would choose one over the other?
Yes. That's the slide on, but I'll stop right now and explain that. Here's the thing. To auto-tune anything, I don't care what it is. If it's got a microprocessor, whether it be a smart valve positioner like we make, whether it be a control loop or anything, it has to be repeatable. Okay? That, again, this is a little bit of artificial intelligence. It's some fuzzy logic, what people call this. What happens is it goes out and it bumps your process and sees how it acts. Then it bumps it again. It'll bump it numerous times and see how to handle that response. It'll bump it and go, okay, let's say it is a flow loop. It'll bump the process and mess with the valve. Bump the process and mess with the valve and see how everything responds and learn from that. If that's not repeatable, it's either going to not tune or the tuning is going to be bad. It's just not going to be good. Okay, when you look at continuous auto tuning, there are people who hate it and people who love it. I'm in between. I've hated it and I've loved it, but here's the thing. It's not going to work on every loop. It's just not. I've had loops where it'll adapt and it keeps adapting, and it is just wonderful. I don't find that very much. I just don't. Things aren't that repeatable. And sometimes, and we're going to talk about wind up and things like that, what happens to that adaptive tuning, sometimes people call it they'll have adaptive deadband. It just gets worse. Okay? It doesn't get better, it gets worse. Remember, the algorithms looks at something, and it has its limitations. It's going to grind through and grind through and grind through. It's assuming things are fixed. Well, they're not. So I hope that answers your question, but adaptive tuning, I've never had that be my best friend. Does it work? Sometimes, but I've never had that be my best friend.
Okay, the second.
Yep. Okay.
The second question we got in is, you might have answered it. Have you found Autotune valuable to get a good starting point?
All right, let's talk about that. Here's what I do. If I go into, whether it's a new controller or an old one or whatever you got, do yourself a favor. If write it down. Get a piece of paper, and let's say I auto-tune, and it gives me a PID. I write it down. Well, I'm going to auto-tune it again. Those numbers won't be exactly the same, but they should be relatively the same. It's in the same ballpark. If they're radically different, if I auto-tune it 5 times and those numbers are radically different, that means the system is not repeatable. It's not going to auto-tune. It's not going to do it. There's just no way. Okay? You're back to PID. You're back to messing with it the old days like I had to do. Now, with that, I'll also say, if you've got a loop and it's running just fine, life's good. It's just do yourself a favor, get in there and write down somewhere, keep PID. Know what that really is. Know what that is. Because believe me, it's going to be in your best interest to know what that is. Especially if you have to manually do this. The other thing about this is, let's say you've got a loop and it's wonderful. You go into a shutdown or some major maintenance going on. You bring everything back up and now your control ain't there. Before you mess with that controller, before you mess with that loop, find out what happened in the field. All it takes is changing a valve out, wrong sizing the valve, a pump impeller, moving a flow meter that was in the right place to the wrong place, and your control's gone. Messing with the controller ain't going to help that. You really need to find out what changed in the process. Now, you're still going to have to, if they can't fix that, you're still going to have to mess with that controller, but at least you know what you're doing and why. I've seen this way too many times where something didn't work in the field and they were in there messing with the controller. If you've got an oversized valve or pump out there, way oversized, you're not tuning that loop. Not happening. Sorry, laws of physics here. It's not going to tune no matter what you do to it. So before you beat on the controls guy, that's the first thing I would look for. Okay? But yes, auto-tune should work, but it's no guarantee there.
The last one we have, it's more of a statement, but maybe you can elaborate. It states, huge challenge is getting operations to understand 1/4 wave tuning and process loop latency will rarely give them a flat line graph, especially with pH and conductivity in process streams. We do the best we can to avoid chasing the PV within an established range. Deadband and output dampening helps.
Absolutely. Well, see, whoever said that obviously has some experience. Yes. What operations and management wants people in white shirts is they want that come to set point and that be a flat line and forever. Well, guess what? Ain't happening. But what he mentioned there was pH. pH is very difficult to control. It's hideously nonlinear. If you told me I got a 5,000 gallon tank of something, and before I can put it back in the river, I have to lower the pH. So here's some acid. And it's got a mixer in there, and there's a pH probe stuck in there. That takes a ramp soak program to do that right. You just can't start adding acid. Why? The chemical reaction, A, is nonlinear. B, it's not instantaneous. I'm going to overshoot every time on a pH loop unless I really get into evolved ramp soak. Add, stop, wait. Add, stop, wait. That's a ramp soak program. You ramp up, you stop, and you see what the rate of change is. You hold right there. And when it quits changing, add a little more. The steps get smaller and they get shorter. That's pretty sophisticated control. But you're right, operations. Now, what also he said was, I'm going to tell the family secret here. What I see all the time is I'll be in a control room and there's, let's say, a flow meter, a mag meter, and it's controlling and the line's nice and smooth and it looks like everybody's happy, but you hear complaints on the product end. Hey, we're not putting enough of this in. We're doing this. It's not exactly good in the real world out here. What happens is somebody wanted to see a flat line and they kept adding deadband until they gave him a flat line. Well, that's great. Except the more deadband you dump on something, the worse control you have. Your control resolution starts to go away. And the dead giveaway is you shut that valve, you shut the valve and you shut the flow off, and it's flowing 400 GPM, 500 GPM, and it's still flowing 500 GPM. And it sits there, and now it starts to kind of tail off to zero. It does that because somebody's piled the deadband on it. Because somebody wanted to see a flat line. Well, I'll give you a flat line, but it's going to cost you control resolution. Like I said earlier, it always costs you something. That's what it costs. And trying to explain quarter wave decay to somebody in operations, well, good luck with that. I've never, they just want to see their flat line. They want to see their pH. They want to see their flow. They want to see what they want to see. And I'm sorry, I'm a controls guy. I can't always give them that because life doesn't work that way. Right here, this slide says Nirvana. Well, yeah, that's Nirvana. You don't always get Nirvana. Sometimes you do. Sometimes you can auto-tune a loop. It comes right up, runs flat. Everybody's happy. That's not always the case. Not always the case. But like I said, you need to always know what PID is in any loop in case you trash your controller, in case somebody makes some changes. You just need to know that. Don't auto-tune. Do yourself a favor. Don't auto-tune and say, oh, great, it's working, walk away. You're going to get bit with that. Know what the controller came up with. Anything else?
Just one last one regarding the pH example. So that pH example, the derivative side of the PID really shines?
Yes. Now, here, okay. Yeah, okay. Yes, pH is one of the hardest things to control. I do a lot of that, unfortunately. Here's the thing. The derivative is crucial. The problem is what people do is when they'll see it overshoot and they start piling on the derivative. Well, again, now you're slowing it down to the point. If you pile the derivative on, you're going to slow this loop down to the point that it's eventually going to either drag where you're basically out of control range, or it's going to start overshooting again because it puts the brakes on so hard, the proportional starts adding more control signal. It's going to be unstable there. The best way to do it, like I said, if you can, is sit down with this and write a ramp soak program. I want to go up, let's say, up one pH of 1. I'm going to go up 1, and I'm going to stop. And I'm going to see how much that keeps drifting. Because, again, I got a chemical reaction going on. That's not instantaneous. It's horribly nonlinear. So I want to see, and when it stops, I'll say, well, once it stabilizes for X period of time, 20 seconds, 10 seconds, however much time you can give me, add a little more, go up a half a pH now, okay? Hold, then a quarter, then an eighth, and that's kind of the way I do it, and it takes some tweaking. That's not going to be something it's just going to happen, okay? But yes, the derivative is your friend in that loop because it's so hideously nonlinear.
That's all we got. Thanks, Wes.
Yes, sir. All right. Temperature control. Again, we talked about this. Majority of things are temperature. Your best friend here is it's slow. Now, what's your worst friend? It's non-symmetrical. If I'm heating something up and cooling something down, it's not following that same curve. Never does. I've never seen it follow that same curve. So if you got somebody out there who's like, oh my God, it ain't gonna. Sorry, it's just not gonna. Things don't heat and cool at the same rate. At least nothing I know of. Okay? So what you really want to do here is you want to say, okay, what is it I'm trying to do? Again, what am I trying to do with this control? All I'm trying to do is maintain set point. Is hysteresis a big deal? Not to me too much. I just want to maintain set point. If that's 100 degrees or 500 degrees or whatever it is, that's my main thing. Okay? Other than trying to worry about the hysteresis. Because a lot of times there's not much I can do about that. All right, thermocouples. We're kind of running a little long here. I'm not really going to talk about this a great deal, but it says when dealing with thermocouples, if I'm a controls guy, why would I care about grounded or ungrounded, cold junction compensation? Because why? Or mounting location? Because that affects the quality of the signal and the accuracy of the signal you're giving my controller. Remember, you give me inaccurate stuff, I'm giving you inaccurate control. This is when you pick up the phone and call your local Gilson guy and said, hey, I need a transmitter. I need a flow meter. I need something. He'll be glad to come out and help you make sure you put it in the right place and it's sized right and it's ranged right. You give me junk and I'm going to give you junk. That's just the way it is. Most of the control, I'll make a statement here that may get me beat up, but I'm going to make it anyway. Everybody's controller works. Everybody's. They work fine. It's the loop itself. It's the instruments. It's the things going on out there that affect it that make it not work. Everybody's controller will work in its envelope, but you give me bad, put a bad thermocouple in the wrong place, and I'm getting a noisy signal, or okay, you're not doing me or you any favors. Pay attention. This is where paying attention to all this stuff will make your control life so much easier. So much easier. It's like whoever asked the question about the pH, first thing I'm going to find out is, let's make sure, maybe it is, maybe it's not. Is that pH probe, or however you're measuring this, in the right place? Is this the best place to get a good measurement? That's the first thing I'm going to look at. All right, RTDs. Okay, there again, when dealing with RTDs, I don't have to worry about the cold junction compensation, but poor dynamic response. What does that mean? Well, it's a little slower. I got to deal with the line resistance, but it is more accurate. So do I use a RTD or a thermocouple? Again, this is when you need to sit down and decide pros and cons, what's best, because the better signal you give the controller, hey, the better it's going to control. And whoever asked that question about adaptive and auto-tune, that stuff's going to work a whole lot better when you give me good signals. That your chances of auto-tuning when you got bad information coming back, pretty much zero. It's worth going up front. It's worth doing the right stuff up front. All right, pressure. Pressure's, a lot of people control pressure. It's fast. What does fast mean? Fast means if I shut down a valve, if I start moving that valve, I'm going to see a not instantaneous, but pretty close effect on my pressure. I start throttling the valve back, pressure's dropping or increasing, whatever it is. So that's a whole different control than temperature would be. The other thing is, you look, it says, how about differential pressure, orifice plates or pitot tubes? Yeah. Are they accurate? Not hideously. I mean, they're not the most accurate thing in the world. They work. In certain applications, that's what you use. But again, if you're giving me a 5% measurement, I'm not going to give you, I can't give you a tenth of a percent control resolution. Not happening. Just can't do it. Okay? And this is stuff that needs to be worked in, excuse me, and thought about when you're tuning that loop. How good can this be? All right. Flow, again, fast, real fast. Now, I'm going to make a couple statements here that might not be appreciated, but it's truth, it hurts. Flow problems tend to always be, more than anything, blamed on the controller. Okay, we can't control this flow. Your controller is no good. It won't do this, it won't do that, it won't do this. Whoa, hang on. Valve's too big, pump's too big. Where are you measuring this flow? Those things, if any of that stuff is off, you're not going to get a flow measurement. And what I'm going to say next is something most people never think about. Flow is a sample measurement. Pressure is pressure. Okay? It's not, if I've got a vessel with a pressure gauge, that's the pressure in the vessel, the entire vessel. Flow's not that way. Whether it's a vortex meter, a mag meter, or orifice plate, I'm not measuring every bit of the stuff coming down that pipeline. I'm just taking a sample and I'm extrapolating it to say, well, if I'm measuring this, then that pipe, all of it's moving that fast. That might not be true. People write books on flow. Maybe this is not as accurate as I think it is. I've got a slurry and it's dragging on the pipe boundary. That's non-Newtonian flow. That could be way off. Well, I'm giving that signal to my controller, okay? And given that signal to that controller, it doesn't know it's off. It's assuming this is all right. Well, what can you expect out of your control then? You're asking for problems. Again, know what's in the field. All right, level control. That's as easy as it gets. If it's not part of the process, if there's a 5,000 gallon tank and it's full of fuel oil, oh, come on. I can do that PI, whatever. It's not critical. I just don't want to run the tank over, and I kind of want to know what the level is. There you go. Again, what gets control people in trouble a lot of times is they go out there and they'll control that tank level, and that's the expectations for every loop in the plant. Now the pH loop comes in. They say, okay, control that pH. That's a whole different animal. That's a whole different thing. Far more complexity. And you may never get to where somebody's exactly happy with that. Again, the nature of the beast. All right. We're not going to go a whole lot into algorithms except to say that the two things you want to take away from this picture, there's no industry standard for PID. The algorithm that Siemens uses or somebody else uses, those are a little bit different. And at the bottom, somebody actually put on this slide, I think it was me, the only way to really tell which one you have of the series, ideal, or parallel is look at the equation of the controller. I don't know anybody who'll tell you that. Most companies, Siemens being one of them, we consider that proprietary. And plus, we really don't want you messing with it. It's big and complex. We don't want anybody messing with that. So they're really not going to tell you. I will say this in all my years of doing this. If I took PID out of brand A's controller and put it in brand B, it worked. Or it was so close it took very little tweaking. So in my experience, those algorithms aren't wildly different. Okay? They're just not. Now, some manufacturers may claim they are. I just don't see that. Like I said, in the old days, if I had to manually tune a controller and I was replacing something else, the first place I started was whatever PIDs were in that original controller. If the customer was happy with that, let's start there. And most of the time, that was pretty close to being dead on. So I cannot see the algorithms being wildly different. Okay. All right. We're going to talk about something here briefly. PID, when somebody says PID control, it could be as simple, again, as your thermostat, or you can start to get complex. The complexity is like this. This is cascade controlling. Ooh, what's that? That's when a controller, you got two controllers, a slave and a master. The master output becomes the input of the slave. Wow, that's complex. Yeah, it is. Why would you do it? Well, if I've got a process that's subject to massive swings or massive upsets, this may be the way to go. The first controller takes over, makes some set point, starts trying to control, giving its output to the secondary controller. So now I've got a basically moving set point that may be more realistic and easier to deal with. At least I can deal with it faster. I say most of the time. Okay. Here it is. There's the goods and bads. Okay. I can control this faster. Generally, I can keep that from really happening to the degree. I can respond so fast sometimes before it completely gets out of hand. I can start controlling it. I can start dampening that back. Okay. And people write books on this stuff. This is a whole different world of control. The downside, again, is complexity. That takes a lot of engineering, a lot of design to make a cascade work well, and most times. Okay. But again, this is not something you just use because you like it. This is something you would use because you have to. Okay. Feed forward versus feedback. Feedback control is, okay, something happened and I'm dealing with it. Feed forward, which again takes more engineering, is I'm looking at a model, and as soon as it starts to change a little bit, I start dealing with it because I know what the model of what happens if I don't deal with it, which is kind of a goofy thing that if you think about it, but it does work. Instead of dealing with it after the fact, I'm going to try to do a little preemptive strike here. The model tells me that if this starts to go at this rate this far, this bad thing's going to happen. I'm going to make the assumption that's going to happen, and I'm going to try to stop it. Again, more engineering, more complexity. All right. Why would I do feed forward? Right here. Those are common applications of feed forward. Now, people talk about, it says like a kiln there. You go to a paper mill and they've got a lime kiln. Well, okay, what are they doing? They're reclaiming the lime, they're burning it, without burning it up, and they're reusing that lime. Well, the problem with that loop is when the lime goes in the kiln, it doesn't come out for 4 hours. So any adjustment I make, I'm not going to know what I'm doing or whether it went up or down or whether I did bad or good for 4 hours. Okay. Feed forward's crucial in that. Crucial. Because I don't want to wait till I make a whole bunch of garbage before I figure this out. Now, is it complex? Yes, it is. But that's the best way. You look at the bottom, feed forward systems are more costly and require more engineering than feedback systems. Sure they do. Is it worth it? Well, you tell me. That's something that you do when you have to. If you don't have to do it, you don't do it. But certain things, again, distillation columns, some boilers and things, I want to control my boiler before it lifts all the safety valves. So I'm going to probably use feed forward if I can. If it's a real small package boiler, it's no big deal, then I wouldn't mess with it. I don't really need it. Okay, ratio and blending. Again, what am I doing? I'm blending two things, or I'm ratioing two things in. Antifreeze. Okay, I'm blending glycol, water, and some coloring. Okay, well, I'm not mixing them in a batch. They're mixed up on the fly. I ratio them in, and I package this stuff, and poof, it's antifreeze. Okay, that's where you get into a lot of that. A lot of blending controllers. We do a lot of this stuff. Okay, complex can be, but generally, again, it's not so bad. It's not so bad because if I've got the right valves or however I'm controlling the ratios or blending, it's not that bad to do. More complex, yes, but still, it's within the realm of PID. Now I'm going to say something here too, that because you have a PID controller on your shelf or a PID card for your system on your shelf, doesn't mean it's capable of everything. This happens quite often. Somebody says, well, I can't do X with my controller. It's because your controller is not sophisticated enough to do that. It wasn't designed to do feedforward. It wasn't designed for cascade. It wasn't designed as a ratio controller. It was just designed as a straight PID loop to do temperature flow or level or something like that. Make sure your controller, your card or whatever is capable of what you're asking it to do. Again, some are, some aren't. Just because it's a controller doesn't mean it does everything. All right. Now, when you tune that controller, some methods lean heavily on experience, while others rely on mathematical considerations. Yeah, that's true. What is good control? Well, you tell me. You're the customer. What exactly are we looking for? What do you expect? It might not be possible. It might, good as I can get, may be as good as there is. It may never be like the pH question somebody had. I don't know. It can be dialed in. It might not be, just because of the dynamics of that system. That bottom line is very crucial. If the loop is not repeatable, we'll not auto-tune. It's just not, it won't. Or the auto-tune so bad it won't be worth auto-tuning. And again, like I said earlier, beware of large dead bands. Somebody couldn't get it to tune. Somebody wants to see a flat line. I'll throw enough dead band to get a flat line. Something else you need to be aware of, most instruments you can do you can add dead band in the instrument. Well, I can add dead band in the system too. Make sure everybody's on the same page here. Make sure you're not adding dead band and the guys in the field aren't adding dead band, because now you got nothing but dead band. Okay? Make sure you know what's going on out in the field with that dead band. Pick a place and add it. When you add it in both places now, you're really not going to get good control out of that. And a lot of people don't know somebody did something in the field. They don't really know what to do with the control system. I personally prefer to pick a place to do the dead band, be it in the system or the controller, or be it in the field, and go with it. That just at least kind of a little standardization there. Then I know what to expect. All right. Controller parameters. It says must be set differently depending on which response is more important. We talked about it earlier. There's a trade-off. It says, in truth, the customer requires both. Absolutely. The customer wants perfect control. Well, good luck with that one. It may not be possible. What is optimized control? Optimized control, fancy word for saying this is as best as it's going to do. I've optimized it. This is all you're going to get out of this system. It's the best that's going to happen. Now, a decision has to get made. Can you live with it? Or do we need to make some changes in the field? Maybe costly changes. Maybe cheap changes. I don't know. But whoever's running this has got to make that decision. All right. Tuning terminology. This has to be understood by everybody. What are you looking for? Okay, what's the resolution? That's the smallest change in the measured value that can be determined by the measuring equipment. We talked about this earlier. If you're going to give me a 5% device, That's fine. Don't talk about tenth of percents to me. You don't have the resolution, okay? The accuracy. How small of a signal can I respond to in my control system? I don't know. You know, I can tell you a basic accuracy. I can tell you an accuracy, but that's based on a lot of things being just right. Repeatability. I'm big on repeatability. If the flow meter tells me this is 400 GPM, and it might not be 400, but that same amount's always 400, I can tune around that. I can say, okay, we all understand that repeatable signal is going to give me the best control. Okay, that's going to give me the best control for your loop because it's constant. Might not be perfect, but it's constant, and I can control to that. I can tune to that. Okay, control quality, sum of all the errors. It is what it is. Okay, I can add this stuff up and say, here's what you can expect, or here's what you got, and that's all we can do. Okay, linearization, conversion of nonlinear relationships to linear relationships. Some things the controller tries to linearize, some things you have to linearize for the controller to make sense out of it. Some things that's just not going to happen real well. pH, salinity being two of them. It's just hideously nonlinear. And there's no reason to try to linearize that, really. Okay? Now, the final control element, that's generally a valve. Pump maybe, but generally a valve. That's what does the work. Okay? If it's not sized correctly, I've said it before, I'll say it again, you're not tuning that loop. Okay? Dead time and dead band get confused with each other. Okay? How fast, the dead time is how fast after an upset can my system respond to that? Okay, that's not deadband. Deadband is added to the input or the output, basically to suppress a very small error signals. Well, I wish that was true. A lot of times people aren't suppressing very small error signals, they're suppressing big ones. Well, again, now your control resolution starts to go away and somebody's not going to be happy. You can show them a flat line, you can show them a smooth chart on the chart recorder, but you're sacrificing control for that. You know, where are you going to put it? Deadband, like I said, you see where it says in the controller and the measuring device. Pick one. Know what deadband's in both sides of the equation here, or you're going to have problems. All right, tricks of the trade. We're kind of running out of time here. If you don't have anything to do during this virus thing and you don't have a life, you can go look up the Ziegler-Nichols method from 1942. That's when things were all mechanical. It's kind of neat to read that, and it talks about quarter wave decay and and that was long before Autotune. So that's how I learned. Okay, that was the rage up until the microprocessor. Okay, that was kind of the place to start. Wasn't perfect, but it was a good place to start. Most people use the closed loop method. The open loop method is not, I don't use that too much because I don't like it. But the closed loop method, I've got my loop, and now everything supposedly is in this loop. I've got my measurement, and I've got my final control element, and I'm going to auto tune if I can. Okay, or I'm going to try to auto tune this. Okay. One thing that I have to caution you is make sure when you push the auto tune button, your process can take that swing, because it's going to start messing with your process. It's going to swing that valve or whatever open and closed. Make sure they can take that swing. If it can't, then you're going to have to do it manually. Then I refer to our friend Ziegler and Nichols. That's worth looking at and kind of understanding where you can get a basic P and I and D from. It gives you a place to start. Also, this may sound elementary, but you need to know with any controller how to abort. You need to know how to stop what you're doing immediately, because I may put a PI and D in there that's way off. I put that controller back in automatic and it starts to go do crazy things. I need to stop it before it screws the process up or hurts somebody. So just make sure you know how to abort. Adaptive, this was a control. This was a question about control earlier. That sounds good. And that sounds good. The adaptive controller, if it's very repeatable, everything works like it should, the adaptive will sort of, it'll work, kind of. But remember, if I have an adaptive controller, everything's fine, and there's a shutdown, and then my guys change a pump impeller or a valve or something like that, that may be the worst thing ever happened to adaptive control. Now you may adapt in the wrong direction. Instead of getting better, it's getting worse. Again, I'm not a great fan of adaptive control. That's just me. That's just me talking. But I'm not a great fan of that. I kind of like the more fixed things I can have, the better I kind of like it. And here's the result of that. It'll wind up. It says, wind up results when the manipulator variable is not able to control the set point, and it resulting in a sustained offset. An example is a very good one. If the control valve won't open, something's blocking it. The controller is going to keep trying, and keep trying. Now, if it's got the adaptive feature, it's gonna wind up. What wind up means is that little bit of error gets bigger and bigger and bigger and faster. Okay? And now people will tell you, well, we have this anti-wind up stuff in our algorithm. Well, good, but it's not guaranteed. Okay? This is the reason that I'm not real big on anything adaptive. I've just seen too many times when it may have been good for a little while, then got out of control. Okay? All right, there's wind up prevention right here. We're kind of past time. I'm gonna have to speed this up a little bit. Turn off the integer when saturation occurs, when a loop is not in use. That's an excellent thing to do. What you'll see is if you leave the controller on and you have a valve out there, I can't tell you how many times I've seen with that valve, it'll sit there, it's off. You know, the power's still on, but there's no flow, and they're working on the plant. That valve will start to go up and down and up and down. And a few hours later, it's going wide open, wide closed, because it's wound up. It's wound up. The controller's not getting a feedback from the flow meter or whatever, so it doesn't know what to do with that. So it's looking around trying to get a signal. So it winds up opening and closing that valve, or turning something on and off and on and off, because remember, it's trying to correct the error. Well, I'm getting zero flow, let's say. Well, I'll keep opening the valve. Well, that didn't work. Now I'm going to close the valve. That didn't work. Now I'm opening the valve. So it doesn't know what to do with that. So it'll wind up. And you see that not as much as you used to, but you do still see it. And it says, like at the bottom, all controllers that employ an integral action can wind up. That's true. Now, steps have been taken over the years to stop that or slow that down, and they have, but it can't never really eliminate it. So it's always there. It's always a possibility. All right. Again, manual versus automatic. I personally like to be able to go into manual and take control of the loop if I have to. I like to start batch or ramp soaks myself. You know, you can have the system do it, but it's nice to be able to start it and stop it when you want to. Is bumpless transfer required? If it is, you need to be able to go in the manual. You need to go in there and take control, move your set point manually, and then take it off automatic so you don't move things too fast. I like that kind of stuff. Now, some people may argue that, but that's the kind of stuff that I like. All right, last slide here. Those of us who grew up in the single loop control world, which I did, pre-DCS, well, with the DCSs, Siemens bought more about 15 years ago, and they made one of the standard controllers in the industry, the 352 and the 353, which we no longer manufacture, but there's still many of them out there. If you need one, if you have one and you need a replacement, Gilson represents our friends here at RetroPack. They make an excellent retrofit, fits in the same spot. It's easy just to pop one in there and get back going again. With that said, I'll answer any questions. If you need help with control, if you have any questions, please call the local Gilson guy. There's one in your territory. He'd be glad to help you. I'll be glad to help you. And if you need control on any level, Siemens can help you with that. And again, I hope you learned something, and I enjoyed it myself, and I do appreciate your time. So if there's any questions, I'm here. Thank you very much.